Okay, this is question 1 from Form A of the 2003 Calculus BC exam. We have a region R which is formed by the curves y equals square root of x, y equals e to the negative 3x, and x equals 1. And part A asks us just to find the area of R. So to find the area, we want to integrate along the x-axis, taking our integrand to be the difference between the curves y equals square root of x and y equals e to the negative 3x. So that means our integrand is square root of x minus e to the negative 3x. Well, we have that now, so we just need to find our limits of integration. We know our upper limit is going to be x equals 1. So we just need to find our lower limit of integration, which I have labeled x naught. How do we find x naught? Well, it's the x value where the two curves intersect. So to find that value, we just need to find the intersection. We need to set the equations of the two curves equal to each other. So we say square root of x naught equals e to the negative 3x naught. And we can use our calculator on this problem. So plugging that into our calculator and solving, we get that x naught equals 0.239. So now we're ready to find the area of R. We want to set up an integral from 0.239 to 1. And we want to integrate square root of x minus e to the negative 3x dx. Plugging that into our graphing calculator gives us an answer of 0.443 for the area. So that finishes part A, which is the easiest part of the problem. Let's move on to part B, which is, in my opinion, the hardest part of the problem. We want to find the volume of the solid generated when R is revolved around the horizontal line y equals 1. So that's this line here, y equals 1. So the integrand is just going to be the cross-sectional area perpendicular to the x-axis of that solid, because we're again going to want to integrate from x naught to 1 along the x-axis. So how do we think about what that cross-sectional area is? Well, if you imagine the x-axis, instead of pointing to the right here, if you imagine it pointing into the screen, then we draw the line y equals 1 as just a point because it goes into the screen. So imagine that's the line y equals 1 extending into the screen. Well, then when we revolve the curve y equals square root of x around that line, we just get a circle. And the radius of that circle, this little guy, is the difference between the curve y equals square root of x and 1. So that value is this, which is just 1 minus square root of x. Likewise, when we revolve the curve y equals e to the negative 3x around the line y equals x, the axis of rotation, we get another circle. Try to make these look like circles. Alright, well, close enough. And in this case, the radius is that. And on the diagram, we see that that value is this distance, which is 1 minus e to the negative 3x. So we have both of our radii of the circles which compose the cross-sections perpendicular to the x-axis. And the area, the cross-sectional area, is the region between those two circles. So how do we find the area of the region that I'm filling in here? Well, we just take the difference of the area, the difference between the area of the bigger circle and the area of the smaller circle. So we want to subtract the area of the smaller circle from the area of the bigger circle. Well, the area of the bigger circle is pi times the radius of the bigger circle, which, as I just noted, is 1 minus e to the negative 3x. We want to square that to make it an area. And then we want to subtract the area of the smaller circle, which is pi times the radius of the smaller circle squared. That is our integrand for this part of the problem. And just like in part A, we want to integrate along the x-axis from 0.239 to 1. Well, we can factor out a pi, and so inside the integral it's just going to be the difference of the squares of the radius. Integrate over x, plug that into our calculator, and our answer is 0.453 pi. Okay, finally part C asks us to find the volume of another solid. This time, the base of the solid is the region R, and the cross-sections perpendicular to the x-axis are rectangles whose height is 5 times the length of the base. Well, we know that the base is R, so we can easily find the length of the base by taking the difference of the two curves. So the length of the base is square root of x minus e to the negative 3x. The height is just 5 times the base, so the height is 5 times that. So our cross-sectional area, which is also going to be our integrand, is just square root of x minus e to the negative 3x times 5 times square root of x minus e to the negative 3x. That's the base times the height of the rectangles, which are cross-sections perpendicular to the x-axis. To find the volume of the solid, we just need to integrate that along the x-axis. Our limits of integration are the same as they've been throughout the problem. In this case, we can pull out a 5 in front of the integrand. And what's left is just this expression squared. We have this times this, which is square root of x minus e to the negative 3x squared, integrating over x. And when we plug that into our calculator, we get that the volume of the solid is 1.554. So that does it for number 1 of the 2003 exam. I hope that this was informative.